Welcome to Computer Science with Sir Baison. Right, today we're diving into an absolute classic. We're tackling a Cambridge A-level computer science question straight from the October/November 2023 paper 32. Specifically, we're zeroing in on question 1, the infamous floating point representation problem. By the time we wrap up this explainer, you are going to be perfectly set up to score some seriously easy marks on this exact type of question. So go ahead, grab a pen and some paper, because we're going to break this down step by step.
Here's how we're going to do it. First, we tackle the classic question itself. Then, we start with the positive version, decode the fractional part, execute the 2's complement flip, and wrap it all up with a quick summary.
All right, section 1, tackling the classic question from the Cambridge A-level paper. Let's get right into it.
So, here's the actual exam problem. It's asking us to convert the decimal number -96.75 into binary, using a 10-bit mantissa and a 6-bit exponent. Now, this specific kind of problem, it's completely fundamental to understanding why computers actually struggle with decimal accuracy. We are literally looking under the hood at how decimal values are stored in a machine's memory.
Okay, let's dive into this target number, -96.75. Now, look, when you first see a negative decimal staring back at you on an exam paper, it can feel a little intimidating, right? But I promise you it's really not. The absolute most important thing to remember here is do not let that negative sign scare you. We've got a highly structured approach for this, and it actually starts by just temporarily ignoring the negative sign altogether.
Which brings us to section 2. Start with the positive, isolating the whole number.
To build some confidence and get our baseline, we always start with the positive version first. We're going to completely drop that negative sign for a second and look exclusively at positive 96. Our first goal, simply figure out the binary conversion for just this whole number.
Notice how elegantly this number breaks down. If we look at 96, we can split that into our trusty binary place values of 64 and 32. Since 64 plus 32 equals 96, well, we just pop a 1 in the 64 column, a 1 in the 32 column, and fill the rest with zeros. That directly translates to the binary sequence 1100000. And just like that, boom, the whole number is totally done.
Moving right along to section 3, decoding the fractional part, where we tackle the decimal.
Since we've successfully isolated and converted the whole number, we're going to transition to the next piece of the puzzle, the fractional part. We're looking at 0.75. Now, you know how whole numbers work, right? Well, fractional decimals have their own incredibly easy logical translation into binary values using fractional place values like 1/2, 1/4, and 1/8.
If we map out 0.75, it's just 0.5 plus 0.25. In binary fractions, 0.5 is represented by a 1 in the very first position after the decimal point, and 0.25 is a 1 in the second position. So, 0.5 plus 0.25 gives us 0.11 in binary format. It's clean, it's totally logical, and it perfectly represents our decimal fraction.
So the crucial point is bringing these two halves together. We take our whole number, 11,000, and our fraction, 0.11, mash them together to get 11,000.11. But wait, because we are building the positive version of our number, we absolutely must remember to add a leading 0. That 0 acts as our positive sign bit. So our complete positive binary string is now 011000.11.
And now for the climax of the explainer. Section 4, the 2's complement flip, converting to negative.
Because our actual target number from the exam is -96.75, we have to transform this positive binary into a negative one. And we do this using the 2's complement trick. Here is your formal 4-step procedural map for 2's complement. Step 1, write the positive binary. Step 2, add the leading 0 for the sign. Well, we've actually just knocked those two out. Now we execute step 3, which is flip the bits. And step 4, add 1 to the end. Let's walk through those last two very carefully together.
All right, executing step 3. We take our original positive binary string, the 0110000.11, and we slowly walk through it, flipping every single bit. The rules are literally as simple as it gets. Every 0 becomes a 1 and every 1 becomes a 0. So that leading 0 becomes a 1, the two 1s become zeros, the zeros become 1s, and our fractional 1s become zeros. That gives us our brand new inverted string, 1001111.00. And this brilliantly illustrates the final mathematical leap. We take that flipped bit string, and for step 4, we add a single 1 to the very end of it. We literally just add it to the furthest right column. That turns our .00 into a .01, yielding our final raw negative binary number, 1001111.01. Honestly, that is exactly how the hardware itself handles the negation.
Let's move into our final phase. Section 5. Summary and key takeaways. Let's secure those marks.
Let's rapidly review the exact steps we just took to convert our value so we can lock this into your memory and pretty much guarantee those exam marks. First, we started with the positive version. Second, we converted the whole number by breaking it into binary place values. Third, we converted the fraction. Fourth, we added that absolutely crucial leading 0 for the positive sign. Fifth, we initiated 2's complement by flipping all the bits. And sixth, we just added a 1 to the very end.
Which brings us right back to our final raw output, 1011111.01. Take a second to celebrate reaching this point, because you earned it. Now, to fully answer the exam's request for a 10-bit mantissa and 6-bit exponent, you'd take this raw binary and normalize it by shifting the decimal point. But getting this raw 2's complement string, that is hands down the hardest part of the battle.
We have successfully converted negative 96.75 into a raw binary string.
So, we've achieved something major here by finding our raw negative number of 1011111.01. But wait, remember those rules of the game we established way back at the start? We are strictly required to use a 10-bit mantissa and a 6-bit exponent. And right now, our binary point is just sitting right there in the middle of our number. So I'm going to leave you with this to think about. How exactly will this raw binary string be normalized, shifted, and packaged to fit perfectly into those strict mantissa and exponent parameters so you can secure full marks on the exam? That, my friends, is the next fascinating piece of this computer science puzzle. Thanks for joining me on this explainer. Keep practicing those conversions, and I'll catch you next time.